I want to dedicate this to my friend and mentor, Norman Fu, who passed away a number of years ago already, but he played a big influence in my intellectual and my personal life. And yes, he's eating a bunch of bugs there, if you can see that on the slide. Okay, so defeasible reasoning. Let me start off then by saying, what would a talk on non-monotonic reasoning be without talking about birds? So I'm going to start talking about birds and specifically penguins. So the general scenario is something like the following. Suppose we have a classical knowledge base that tells us that birds fly, birds have wings, robins are birds, penguins are birds, and penguins don't fly. Then, of course, if you take this together, all that information, and you look at it from a classical perspective, you can conclude that penguins can both fly and don't fly. So in some sense, this says that there are no penguins if you're in the classical scenario. Now, there are many solutions to try and solve this kind of incoherence or inconsistency. There's belief revision, for example, as well. But non-monotonic reasoning, and particularly the form of non-monotonic reasoning that I'm going to talk about today, defeasible reasoning, takes the view that when we make these statements, such as that birds fly, what we mean probably is not that there are no exceptions, but rather, for example, that birds usually fly. So the idea is to extend the language that we have in some way. If you look at the previous knowledge base, most likely the correct kind of translation would be that birds usually fly, birds usually have wings. Maybe statements 3 and 4, there are still classical statements. That's up to the modeler. And then penguins usually don't fly. And then the question becomes, if you have this more extended language, what are the consequences that can be or ought to be derived from such a knowledge base? If I look at, again, at the moment, just intuitively, I think most of you would agree that for something like this, whatever usually means from a technical point of view, what you probably would want to be able to conclude from this is that robins usually fly and that robins usually have wings. It seems to be fairly non-controversial. But with penguins, it might be slightly different. If you ask yourself, should I be able to conclude that penguins usually fly and that penguins usually have wings? I would argue that, again, the statement about penguins usually flying, most people would agree that you should not be able to conclude this. The answer intuitively being that we have some specific information that says that penguins usually don't fly. But what about penguins usually having wings? Now, here we come to at least 2 ways of looking at the problem. So the way in which I'm expressing this at the moment goes back to an intuitive explanation of Daniel Lehmann's. He referred to one version of reasoning, such as this, called presumptive reasoning. And under this type of reasoning, you would conclude that penguins usually have wings. The argument would be that since there's nothing that kind of conflicts with this, this is a reasonable way of drawing a conclusion. But there's a slightly different approach to this as well, and this was termed by Lehmann as prototypical reasoning. And the argument intuitively with prototypical reasoning is to say, well, we know that penguins are not typical birds by virtue of the fact that they don't fly. So does it really make sense to then attribute the default properties of birds to penguins as well? So under this type of reasoning, one would argue that you should not be able to conclude that penguins usually have wings. So I'm not arguing for one of these 2 forms of reasoning as being better than the other. I'm simply saying that at least intuitively, the moment we move away from classical reasoning, entailment becomes an interesting question in that there might be more than one way of looking at correct forms of entailment. Interestingly enough, at least intuitively, but in the end we'll see technically as well, presumptive reasoning is usually stronger than prototypical reasoning. In other words, you can conclude more if you're making use of presumptive reasoning. So I would say that, quoting the author Douglas Adams, that defeasible reasoning, well, firstly, it's an ongoing area of research, but a nice way to summarize it is to say that we demand rigidly defined areas of doubt and uncertainty. So we want to talk about doubt and uncertainty, but we want to formalize it properly to get a sense of exactly when and under what circumstances we should use particular entailment relations. So it is an ongoing area of research. It's been around for a long time. Recently, let's say in the past 10 or maybe 15 years or so, this is it originally started in propositional logic with propositional logic as the basic logic, but it's been applied to other forms or other versions of logic as well. And as you'll see a bit later in my talk, I'll talk, of course, about its link with description logics. So as I pointed out, there are different modes of defeasible reasoning, different forms of entailment, if you like. What's nice about the particular approach that I'm going to look at is that it can frequently be reduced to a series of classical entailment checks, which means in the end that if you have an efficient entailment checker for your particular logic, this is something that you kind of just place on top of that, with a nice formal underpinning and a nice formal explanation of why this is an appropriate way of doing things. Okay, so let's try and make this a little bit more formal. I'm going to go back to the way in which the original originators, I guess, of this form of reasoning looked at this. They looked at the term usually as a form of a consequence relation. So if I want to say that birds typically fly, I would use this twiddle symbol to indicate it's a form of a conditional, if you like. If I look at the knowledge base that I had a little bit earlier, or the informal expression of the knowledge base, then what I have on the slide now is how that would be presented. So birds usually fly, birds usually have wings. If I want to make statements about classical statements, it turns out, and again, I'll show you in a short while, in a slide or two, why that's the case. Classical statements can be kind of reduced to these conditionals as well. Essentially, what this is telling us is that if I want to make a classical statement, for example, that robins are birds, then what I do is I take its negation as the antecedent of such a conditional, and I put bottom on the right-hand side. And that's essentially saying that it's not possible. It's not possible for something or for the statement robins are birds not to be true. Similarly, then, if I want to express that penguins are birds, I'll do it in the same way. And then the last statement there simply indicates that birds typically don't fly. So it's really just at the moment, just syntactically speaking, a way of translating the kind of informal expression that I had previously into something formal. Now, this dates back, as I say, to the 90s, and the originators of this way of looking at non-monotonic reasoning was Kraus, Lehmann, and Magidor. So what they did at that point is, as I say, they looked at this form of defeasible or non-monotonic reasoning as a conditional, as a consequence relation starting off. And the idea was to, rather than just implement some particular system, to take a step back and look at what this type of consequence relation, what properties it ought to satisfy. So the first class of properties I'm going to look at the moment on this slide is frequently known as system P. So for example, the first property there is simply reflexivity. It's saying that usually if alpha, I should be able to conclude that alpha is the case. Similarly, the second one is an easy version. It's also easy to understand. If I have that if alpha, then usually beta, and if beta is classically stronger than gamma, then I should have that alpha. Usually if alpha, then gamma as well. So some of these you will recognize if you've looked at any kind of proof system. So and or, for example, are well-known examples of kind of proof rules. In this case, you can think of them as postulates or properties. But of all these, probably the most interesting one for our purposes is the last one, cautious monotonicity. That is simply as the name indicates, it's simply a weaker form of monotonicity. So it's saying that if it's the case that if alpha, then usually beta, then I can strengthen my antecedent. In other words, I can add gamma to my antecedent. So in that case, I would just have monotonicity. But this is simply saying as long as it's also the case that if alpha, then usually gamma holds. So I have an additional kind of constraint there. So what's the point of all these properties? It's a way of saying that this is what the twiddle consequence relation ought to satisfy. And then there's a way of extending this. A second kind of way of looking at this that's a little bit stronger. In this case, we have all the same properties except right at the bottom. Instead of cautious monotonicity, we have a slightly stronger form of monotonicity referred to as rational monotonicity. So there again, you can see that it is a form of monotonicity. It's saying that you can strengthen the left-hand side or the antecedent. But in this case, the additional condition is weaker and therefore the property itself is stronger. The additional condition simply says that if alpha, then it should not be usually the case that not gamma is the case. And then I can add gamma to my left-hand side. Okay, so basically now these are two classes of properties. So they don't specify a particular meaning for the consequence relation twiddle, but it's saying that if you want to give a meaning to something like this, the claim here is that they should satisfy these properties. And depending on whether you adhere to system P or system R, that would it would need to specify the specific properties related to that particular system. Okay, so what does this help us when we come and when we want to actually construct matters and look at a particular interpretation of the twiddle consequence relation? Well, we can give it a kind of a semantics in the following way. So what I'm going to do is I'm going to focus on the stronger one, on system R, and not on system P. So one way in which to give this a semantics is via ranked interpretations. Now, there are many ways in which to actually formalize this. The one I've chosen here, it's referred to as ranked interpretation. So basically what we have is a function from our class or set of valuations associated with a particular propositional logic. And that function goes to the natural numbers and we add infinity to it. Then there's a convexity property that essentially says that you can think of this as assigning ranks to all the different valuations that I have. So the convexity property simply says that there are no kind of empty levels here. That's not particularly important. This is frequently also represented by ordinal conditional functions. But really, in the end, what we're interested in here is a form of a total pre-order over all the valuations. And the intuition is that you have the lower down in the ordering, the more typical or preferred a particular valuation is. And then we have the, and of course, the higher up they are, the less plausible or preferred they are or typical they are. And then we have the extreme case if we assign infinite to a particular valuation, that's saying that that world is impossible. So that's the basic setup over here. And the point is that from this, we can generate, there's a fairly straightforward way of generating a particular consequence relation from this. So the basic idea is simply to say that if I have such an ordering and I look at a particular conditional, if alpha then usually beta or alpha twiddle beta, then I'm going to say that that holds given this ordering or given this function, this ranked interpretation, if and only if the most preferred models of alpha are also models of beta. So it's a very straightforward way of looking at things. What's nice about this particular representation about the properties that I talked about earlier as well is that we have a form of a representation result that essentially tells us that any twiddle, any consequence relation that satisfies all the properties of system R can be generated by a particular total pre-order or ranked interpretation. And conversely, any ranked interpretation that we can use to generate such a consequence relation, the consequence relation will satisfy the properties. So it's a nice way of semantically expressing what the properties were telling us. Okay, so that was the initial work by Kraus, Lehmann, and Magidor. And then soon after that, a subset of the authors, Lehmann and Magidor, rephrased things in a slightly different way. In some sense, what they did when rephrasing it was to look at the consequence relation more as an object level connective, if you like. So it's still not quite on the level of propositional logic, but the idea is to look at kind of an extended language in which you have, and in this case, I've indicated this by the squiggly arrow, and I want to distinguish it from the twiddle because now it's an object level connective and not a consequence relation. But technically, it's not that different from the consequence relation. Again, what we can do is if I have these ranked interpretations that I talked about earlier, I can provide a semantics for the language that includes this squiggly arrow, this form, this conditional that's supposed to indicate usually or typically. And the semantics for that is precisely what the consequence relation would have told us. If I have a statement of the form alpha squiggly arrow beta, then I'm going to say that it's true in the ranked interpretation if and only if the most preferred or the best models of alpha are also models of beta. So as I say, you can think of this as a version of, as a slightly extended version of propositional logic. If you look at this semantics that I've given it, and you think about it for a minute, it should be reasonably clear that I can express classical statements in the semantics as well. By classical statements, I mean if I take a classical propositional statement, I would regard such a statement as true in a ranked interpretation if it's true in all those worlds that get a natural number as its rank. In other words, I exclude all the worlds that have infinite as its rank, and if I retain all the others and alpha is true in that, I would say that alpha is true in that ranked interpretation. And the same thing can be expressed by saying that not alpha squiggly arrow gamma must be true in it. So in that way, you can think of this semantics as being able to express classical statements as well. Okay, so the moment we do this, now we're closer to what our original goal was, and that is to be able to have a knowledge base in which you want to express this idea of usually. So going back to the birds example, my knowledge base would now be, well, if I allow for classical statements, it would be the first one that you see on the first blue block there. So birds usually fly, penguins usually don't fly. Then I have two classical statements, penguins are birds and robins are birds. And finally, birds usually have wings. So this is one way of expressing it. If I'm keen to not, if I'm keen for all my statements to be conditionals, in other words, to have the squiggly arrow in the middle, then as I've just indicated, or as I've just shown on the previous slide, I can take those classical statements and I can rephrase them as conditional statements. In other words, penguins are birds can be rephrased as not penguin implies birds, squiggly arrow bottom. So this would then be a formal expression of the original knowledge base that I was talking about informally when we started off with this. But of course, this doesn't yet tell us how to draw conclusions from this. So before I look at exactly how to do that, the idea, of course, is then in the end that the central question that we're trying to answer is, if I have a knowledge base of this form that I've just described, our central question is, if I then look at any statement in my enriched language, can I determine whether this logically follows from the defeasible knowledge base, whatever logically following means, right? And this is what we're trying to define here. So essentially, we're trying to define a form of defeasible entailment. So just to make this more concrete, if I have the knowledge base that I was talking about at the moment, initially I asked the question, should we be able to conclude that robins typically have wings or that penguins typically have wings, for example? So this is the formalization of that question. That's the question we're trying to answer. So the first attempt to provide such a form of entailment is to do what you do in the classical case, right? So in the classical case, standard entailment simply says that if I have a knowledge base and I have a statement on the other side and I want to know whether the statement is entailed by the knowledge base, I would look at all the models of the knowledge base and I would check whether the statement is true in those models. And if it is, I would say that the statement is entailed. So the question is, perhaps we can do this over here as well. So our semantics in this case, in the extended language, is not one of classical valuations, but one of these ranked interpretations. But nevertheless, we can try and use the same taskier notion, which would mean that if I have a knowledge base K and I have a statement of the form alpha squiggly arrow beta, I would look at all the ranked interpretations in which all the statements of K are true. And we know how to do that. That was defined on the previous slide. And then I would check whether alpha squiggly arrow beta is also true in all those ranked interpretations. So it's a perfectly fine definition from a technical point of view, but it has a few problems. So the first problem, if we look at examples, is that it really doesn't give us the results that we would want it to have, just even from an intuitive point of view. So for example, if I have a knowledge base that tells me that robins are birds and that birds usually have wings, I would say it's reasonable to, from an intuitive point of view, to be able to conclude from this that robins usually have wings. But this form of entailment cannot do that. Here's a counter model. In other words, here's a ranked interpretation in which the statements in K are true, but in which the statement R, squiggly arrow W, is not true. So at least already from an intuitive point of view, we can see that this is probably not a good idea, but there's a more general reason why this is not a good form of defeasible entailment or non-monotonic entailment. And that's because the entailment relation is actually monotonic. It should be easy to see that this is the case because it's a Tarskian form of entailment, right? In other words, what do I mean by monotonic in this case? If I add anything to my knowledge base K, I won't be able to lose any of the consequences that I've drawn previously. It is non-monotonic in the sense of on the level of the squiggly arrow. So in other words, if I take a particular statement and I strengthen its antecedent, then things are different. But on the meta level, on the level of entailment, it's monotonic. So it's not a good way of doing things. That's not to say that this is a useless form of entailment. It's frequently viewed as kind of the core of any non-monotonic or defeasible form of entailment. But nevertheless, it's not really what we would want. So what I'm going to do then is I'm going to look at one form of defeasible entailment that is actually non-monotonic, and that, well, as you'll see in a moment, it conforms to these properties that I've talked about a little bit earlier. So what Lehmann and Magidor did when they initially looked at forms of defeasible entailment, their point was, or their claim was, that the way in which you should define this form of entailment should link up with this rationality properties that were specified. So more specifically, if you look at a knowledge base and you look at all the consequences of the knowledge base, that would be a bunch of statements of the form alpha squiggly arrow beta. If you think of this as a binary relation, you can think of it as a consequence relation, and then suddenly you can apply these properties directly to them. So essentially the Lehmann and Magidor thesis was that if you look at this as a consequence relation and you compare it to these rationality properties, then it should satisfy everything in system R up to rational monotonicity. So that's kind of the litmus test that they're thinking of in terms of whether this is a reasonable form of entailment. It's fairly clear to see that the form of entailment that I've just looked at is not a rational consequence relation. It doesn't satisfy these properties. I'm not going to go through the details, but essentially it doesn't satisfy rational monotonicity. And what I have on the slide there is an example that shows exactly that. So the point here in the end is you may or may not agree that all those properties are reasonable, but the moment you subscribe to those properties, then it's a nice way to, if you want to define a particular form of entailment, to check whether it actually conforms to those properties or not. So as I say, what I'm going to do is I'm going to look at one of these. So this goes by various names. I think originally this is something that was devised by Judea Pearl. He referred to it as System W. Kraus, Lehmann and Magidor came up with essentially the same thing. That was, I think, more or less at the same time as Pearl. They refer to it as rational closure. If you want to look at it from a semantic point of view, it's probably best described as minimal ranked entailment. So here's the basic idea. If I look at these ranked interpretations that I've talked about, the intuition underlying this form of entailment is to say that we're assuming that things are typical unless they're not. So it's only if we don't have a particular reason to think of a particular world, if you like, as typical, that we're going to deviate from that. So we can formalize that process by placing an ordering over the ranked interpretations. So what does this ordering do? The idea is to say that any ordering in which worlds are pushed down lower, in other words, in which there are more preferred worlds or worlds that are more typical, that I'm going to prefer over any of the other worlds. So the way in which this can be formalized then is to say that if I take any two ranked interpretations, let's say R1 and R2, then I'm going to say that R1 is at least as preferred as R2, if and only if for every one of the classical valuations, the rank that R1 gives that classical valuation should be at least as typical or at least as good as the rank that it's given by the second one. So this gives us a partial order. It's not a total pre-order, but there's a very nice result that the first version of this already occurred in 1998 by Booth in Paris, but it was very nicely set out by Laura Giordano, who's, I think, somewhere, at least she's a flock. Hi, Laura. In 2015 in an AIJ paper. So the result essentially tells us that if we take any defeasible knowledge base and we take its models and we place this ordering over the models, then this ordering is going to have a unique minimum. So a single ranked interpretation associated with that knowledge base. So it's a very nice technical result. The reason it's useful for us is we can use this then to define defeasible entailment. So what we're simply saying then, this form, semantically speaking, this form of entailment says, give me a knowledge base, look at the ordering that I've just described. This ordering will have a minimum, as in other words, a unique ranked interpretation. And then whatever statement or whatever statements are true in that particular interpretation, I'm going to take those statements as exactly what entailment means in this particular case, which seems quite reasonable from a semantic point of view. So yes, the definition is what I have at the bottom of the slide there. I can give you a couple of quick examples as a way of indicating that this is a reasonable way of doing things. But actually, before we look at the examples, because we have a single ranked interpretation that describes our form of entailment, it immediately follows from the previous results that I gave that this is rational. In other words, it satisfies all those properties of system R because of the representation result that I mentioned a little earlier. So that gives us kind of a technical reason for using this form of entailment as well. But if you want some intuitive indication of why this seems to be reasonable, if I have a knowledge base that just says that birds usually fly and penguins are usually birds, then from this I would get the transitive result, if you like, that penguins usually fly. Similarly, if I replace penguins usually are birds with penguins are birds, then when it comes to the non-monotonic part, if I add to that penguins usually don't fly, then I lose the consequence that penguins usually fly. If I add that robins are birds, then initially, well, I will get the result that robins usually have wings, which seems reasonable as we indicated earlier. But secondly, when we come to penguins, this form of entailment would conclude that it's not the case that penguins usually have wings. So this corresponds to the prototypical form of reasoning that I mentioned a little earlier. So there are other forms of reasoning that would correspond to presumptive reasoning as well, lexicographic closure being one of them, but I'm not going to go into the details for that. For now, we're focusing on, or for the purposes of this talk, we're focusing on rational closure. Right, so this is all definitional. So I hope I've given you some indication of the semantics of this form of entailment and also some motivation for why this is a reasonable way of doing things. But now I want to move to the computational aspect. So there's a nice algorithm. Remember right at the start, I was saying that the form of defeasible reasoning that I'm going to talk about frequently kind of can reduce to a series of entailment checks. And this is precisely what I want to look at now. So let me first give you an indication of how the algorithm works on a high level, then I'll quickly show the algorithm, but I think what's much more instructive is to look at a particular example to give you an indication of how this works. So the way in which this works is as follows. You get a defeasible knowledge base as your input, and a defeasible statement, alpha, squiggly arrow, beta, and you want to know whether that statement follows from the defeasible knowledge base. So what the algorithm does is it starts with the defeasible knowledge base, and it ranks the statements in that defeasible knowledge base. It ranks them in a very systematic way. The intuition is that the more specific the antecedent is of any of my statements, the more kind of entrenched it is in the knowledge base. So for example, if I know that birds fly but penguins don't fly, then if I know that a penguin is a bird, the statement that penguins don't fly is going to be ranked higher or more entrenched in the knowledge base because it's more specific, if you like. It's the principle of specificity. So there is an automatic way in which to do this. Essentially, and I'm not going to go through all the details here, but essentially the idea is that I look at my initial knowledge base, I take all my squiggly arrows and I turn them into material implications. And then from these, I identify all those statements whose antecedents conflict with what I know from a classical point of view. And I'm going to regard those as more exceptional. Then I'm going to take those out, and then I'm going to keep on doing the same process iteratively. You'll see in a second when I look at an example exactly what this means. From such a construction of these sets of exceptional statements or more specific statements, I can then go back and rank statements. And in the end, then I'm going to use this ranking to determine what to do when there's a conflict from kind of a classical point of view. Okay, so as I say, this idea of computing exceptionality, what it corresponds to in the end is, so there's a nice theoretical reason for looking at this or looking at this particular way of defining exceptionality. I'm going to say that a classical propositional statement alpha is exceptional if, when I look at preferential consequence, if the statement top twiddle not alpha holds in it, then I'm going to regard it as exceptional. And there's a nice little result that shows that this actually corresponds to saying that if I look at the classical version of my knowledge base and the negation of alpha follows classically from that, then I'm going to regard alpha as exceptional. And if I then want to look at whether defeasible statements are exceptional, that corresponds to whether their antecedents are exceptional. So this is how we'll define exceptionality for a specific statement, and then we'll go through a whole process of identifying these. So here's the algorithm, but as I say, I'm not going to go through this in detail. What I'd rather do is look at a particular example and show you what this actually means. And I'm going to go back to the birds example, of course. Something that I should mention before I go through this, I've mentioned more than once now that we can have classical statements in here if we want. So for example, in this particular rendition, I have the statements that penguins are birds and that robins are birds. You've also seen that I can convert these to conditional statements or defeasible statements as well. But it turns out that anything that's classical are always going to be exceptional, which intuitively makes sense because it's basically saying that they are so entrenched in the knowledge base that you can never throw them out. So just bear that in mind as we go through this example to give you an indication of how this works. Okay, so as I say, here we have our initial knowledge base K. Then what we do is we set the set E0 to be the whole knowledge base. And now what we want to do is we want to identify all those statements that are exceptional with respect to this knowledge base. So in this case, we have 1, 2, 3, 4, 5 statements. The two classical statements are going to be exceptional. They're always exceptional. The way in which to do this then, let me see if okay, no, I haven't done that, is to look at classical versions of these squiggly arrows and ask ourselves, if you look at the antecedent of any of these statements, does the antecedent follow from the classical version of the knowledge base? So in this case, if I look at the statement that penguins usually don't fly, if all these are made classical, it should be easy to see that not P is a consequence of the knowledge base that I have here. And therefore, P is exceptional, and therefore that statement, the statement P squiggly arrow not F, is going to be viewed as exceptional. All the others, the two remaining ones, have B as their antecedent, and B is not exceptional. So not B does not follow from the classical version of what we have here. So what that means is for the set of exceptional statements, we include the classical versions and then the statement that says penguins usually don't fly. Now we do the same thing, but we do this with E1. Well, in this case, there is nothing that's exceptional because we've removed from a classical point of view the reason for exceptionality. P is still exceptional. So We move that out, and we have the two classical statements at the bottom. And then we reach a kind of a fixed point. So once we have the classical statements at the bottom, they're never going to be removed. So we stop, and from this we can then work back in using these three classes or three sets that I have to come up with a ranking of the various statements. So the ranking in the end tells us that those statements that are always exceptional will get a rank of infinite. So that's the two classical statements at the bottom there. The statement that penguins usually don't fly has the rank 1, and the two statements with B as its antecedents has rank 0. So intuitively what this tells us is that if there's any conflict from a classical point of view, if you like, we would need to remove statements that have a lower rank in here. So in other words, I'm going to remove the statement, for example, that says that birds usually fly before I remove the statement that penguins usually don't fly. So that's the intuition associated with this. The nice thing, as I said about this, is that this way of defining or ranking the statements is automatic. There's a very specific way in which to do this, and it applies to any knowledge base. Okay, now we have a ranked knowledge base, but it doesn't yet tell us how to conclude whether a particular statement is entailed by our knowledge base or not. So it turns out that it's relatively easy then from an intuitive point of view to understand what's going to happen. So the idea is the following. If you give me a particular statement, alpha squiggly arrow beta, what I'm going to do is the following. I will look at the ranked knowledge base that I have, but the classical version of that. So the first thing I'm going to ask myself is the antecedent of my query consistent with the classical version of the full knowledge base that I have? If it's consistent, then I can just do classical entailment checking. But if my antecedent is inconsistent with the knowledge base as a whole, then it basically means that there's a version of a conflict. And then the question is, what do I do? So it turns out that for rational closure, what rational closure dictates you should do is you should take all the statements on the lowest level, rank 0 initially, and remove them. And then you ask yourself the same question for the slightly smaller knowledge base. Is the antecedent of my query consistent with that or not? If it's not consistent, then I'll remove the next level of statements and so on and so on. So essentially, I retain as many of these ranks as possible while keeping the antecedent of my query consistent with the knowledge base. Once I've reached that point, I can just ask the classical question, and that will give me the final result. So again, I've given you a very high-level description of this, but examples are usually much better to give you an indication of how things work. So if I go back to the birds example, we've already seen that if I look at that knowledge base, it will be ranked in the way in which I have on the slides over here. So if I now ask the question, do robins typically have wings? The first thing the algorithm would do is it would check if my antecedent R is consistent with the classical version of my knowledge base, right? And it is. So that means to answer the question whether robins usually have wings, to answer that question, what I simply need to do is check whether the classical statement R implies W holds in the classical version of the full knowledge base that I have, and it does. So therefore, I can conclude that robins usually have wings. There we go. How about penguins having wings? I'm going to do the same thing. I look at my antecedent, P, and I check whether it's consistent with the full knowledge base that I have. It's not. Its negation is implied by the classical version of the knowledge base that I have. And then rational closure tells me to remove the first rank of statements. In other words, those two statements at the top. And now I ask myself the same question, but with a smaller knowledge base. So the question is the antecedent of my query consistent with the remainder of the knowledge base or not? In this case, it is. And now I can ask to get an answer to the question whether penguins usually have wings. I simply need to check whether the classical version of this, that penguins implies W, is true or not. And in this case, it's not true. It's not true because I've kind of removed the reason, of course, for there frequently being a conflict on rank 0. So in this case, the answer would be no. Okay, so I've talked for 40 minutes already, and I haven't said a single word about description logics. So, at this point, probably the NMR people are telling me, but you know all of this stuff. We know all of this stuff. Why have you told us this? And the description logics people are saying, okay, great. What about description logics? So I'm finally getting to description logics. So there's an obvious way, in some sense, to look at defeasibility in the context of description logics, and that is to look at subsumption, classical subsumption statements, and to defeasify them, if you like. So this is the idea. What we're going to do is we're going to, in this particular case, I'm going to focus on ALC, and I want to look at an enriched version of ALC, defeasible ALC, where you have a defeasible form of subsumption. That's the only difference between classical ALC and defeasible ALC from a syntactic point of view. And of course, by now you would guess that the intuition is that this is supposed to mean that usually C is subsumed by D, or that normally C's are D's. Simple example, I'm not going to go through this in a lot of detail, but you get the point, I think. If I know, for example, that employee students are defined as all those students that are employees, then I would be able to express statements such as that students usually don't pay tax, but employee students pay tax, but as an exception to that, employee students that are parents don't pay tax. So we have exceptions to exceptions, very similar to what we had in the propositional case. It turns out that it's relatively straightforward to take those properties that I mentioned in the propositional case and lift them up to the description logics case. You'll see that basically all of these, except the one at the bottom that I have there, are really just description logic versions of the propositional properties that I indicated previously. At the right there at the bottom, I have cautious monotonicity. Right at the bottom, I have a property that's called consequent or consistent, cons in this case. It simply tells me, and you'll see why in a second, this is something that is needed in the description logic case. It's saying that top, it's not the case that top is usually subsumes bottom. It essentially, in the end, ensures that when we look at interpretations, the first order or DL interpretations, that our domains are non-empty, which is the standard approach, of course. But I'll get to that in a second. So there are some derived KLM-style properties that actually specifically refer to existential and universal restrictions. But note that these are derived properties. You can get them from the properties that I've already expressed. And similarly to the propositional case, we can stop with cautious monotonicity, or we can strengthen matters a little bit and replace cautious monotonicity with rational monotonicity, which I've done on this slide. So this is all just to show that it's a fairly straightforward exercise to take what we had in the propositional case and lift it to the description logics case. Similarly, there are derived properties over here. But here's, in my view, the more important bit of what we're doing over here. The question is, from a semantic point of view, how should we lift what was done in the propositional case to the description logics case? So you may remember that intuitively, in the propositional case, we took a set of all propositional valuations and we ranked them. We gave them a ranking. There was the ranked interpretation function that did it for that, that did that for us. But that was essentially an ordering over the possible worlds or the valuations that we used. So an obvious way to try and do this in description logics is to place a ranking over the first order interpretations that we're using as well. And it is possible to do that, but it turns out to be fairly messy in my view. There is some work that does exactly that. But there is a slightly different way in which to do this, and that is to say that instead of ranking the first order interpretations, what I can do is I can look at a particular first order interpretation and I can rank the individuals in the domain of that particular interpretation. And this is essentially what I have over here. So the definition is there. I'm talking about modular orderings and modular interpretations, but essentially the intuition here is that what we do is give me a specific first order interpretation, and I'm going to extend that interpretation by adding an ordering, a total order in this case, over all the elements of my domain. And that I'm going to use then to, well, okay, here's an example of something like that. The way I'm going to use that is in the same way in which we can kind of think of the propositional case as extending propositional logic. This can be thought of as an extension of ALC. The only thing that we need to provide from a semantic point of view is the meaning of defeasible subsumption. And with that ordering, we have exactly what we need for that. give me such a ranked interpretation. If you give me a defeasible subsumption statement of the form C is usually subsumed by D, then I'm going to say that that is true if all the minimal or most preferred elements in my domain that are also in C, in the concept C, are also in the concept D. So it's in that sense, it's a fairly straightforward extension of what we did in the propositional case. So it turns out that defeasible ALC has the finite model property, which makes things very nice for us. Again, I think Laura and her colleagues proved this initially. In terms of these properties, we have a similar representation result, which tells me that for any ranked first order or ranked interpretation, if you look at the meaning in which we assign to defeasible assumption, it satisfies these rational consequence properties. And similarly, if I look at any way of interpreting defeasible subsumption using these properties, I can find a ranked interpretation which corresponds exactly to that. Okay, so how does all of this help us in the end? It turns out that we can then do something very similar to what we did in the propositional case. You may remember that in the propositional case, we ordered all the interpretations and found that we could get a unique minimal interpretation, ranked interpretation, and that would be the basis for our form of defeasible entailment. We can do something similar in the DL case. It doesn't work out so nicely. There isn't a specific minimal one. But if we look at fixed domains, we can do the same kind of thing for all those interpretations with the same domain. We can order them and find unique ones. And again, I'm not going to go into the details of that, but there is a construction that tells us that if we look at what's true in all of them, we're going to get something that's very similar to the propositional case. I will say a bit more about this in the talk just after the tea break. It turns out that I'm the next one that speaks in the session just after the tea break. So if you're interested in the details, you can come to that talk, of course. This is not an advertisement, I'm just mentioning that. So as I mentioned, there isn't a unique model, but there's something very closely related to that. And it turns out that the algorithm that I described in the propositional case, there's something very similar, an algorithm that's very similar to that works for ALC as well. There's a little bit of extra technical work that has to be done, but the gist of what we're doing is exactly the same. So we get something that's very useful there. So on the one hand, it seems like a success story because it all works very well. We've just taken the propositional stuff, we've lifted it to the description logic case, and we get what we want. But do we really get what we want? And the answer is no. And the people who initially showed this, one of them is sitting in the middle here. So this is Annie with her student, Maximilian Penzel. Okay, so actually, before I get to that, so far I've just talked about, in the description logic case, I haven't mentioned A boxes at all. I've just mentioned T boxes. So if you just restrict yourself to T boxes, things work really well. And in fact, we can show that if a knowledge base does not contain role assertions, then we can have this rationality result, that it satisfies all the properties. So it's in that sense, it's a really nice result. Things do get a little messy when we get to A boxes, though. So I think I am running out of time, so I'm not going to go through the details, but it turns out that the moment you introduce A boxes, you don't have this nice, unique, minimal result that you normally get, which means it translates in the end to the fact that the entailment relation you get is not rational. In particular, it doesn't satisfy the rational monotonicity property. Now, again, one could argue whether you want this or not, but the point is that if you do want it, then you would need to do something else. So one could still say that this is a nice success story because at least it works well for T boxes, but this is where the work by Annie and Maximilian Penzel came in. They showed that rationality, as we've defined it here, is not really sufficient because it really only focuses on the Boolean or propositional aspects of what we've done. And this example explains it, I think, very nicely. So this is shamelessly stolen from their paper, or a version of this at least. So if we have a T box in which we have a statement that says, classically speaking, if you're a boss, then you're a worker that doesn't have a superior as a worker. Okay, and then if you're a worker, then you typically have a superior that's a boss, and bosses are typically or usually responsible. Then from an intuitive point of view, it seems reasonable to be able to conclude that if you're a worker, you have a superior that's responsible. But it turns out that with rational closure, as we've described it, you can't. And the main reason for this is that the moment you go across the existential quantifiers, you kind of don't get what you want. So again, I know I'm running out of time, but if you look at the interpretations, the two interpretations that I have at the bottom here, you will see that the one on the left has an arrow that goes to what is essentially an individual with certain properties in the concepts that's not a boss, that is responsible, and that's a worker. There's an arrow that goes from that to the object at the top. And in the second interpretation, there's an arrow that goes to the second element. Now, think of these little boxes that I have as ranked interpretations. So the higher up the individuals are, the less preferred they are. So the crux of the matter here is that what we would, semantically speaking, want is in the same way in which we want to push down individuals, or let me rather put it like this. In the classical case, we wanted to push down worlds as much as possible to make them as typical as possible. In the DL case, this translates to pushing individuals down as much as possible so that they're as typical as possible. But the moment you have an existential restriction, what you want to do is the arrow that goes out of a particular individual, you want that to go to an individual that is as low or as typical as possible as well. And what we have at the moment, the properties doesn't properly correspond to that because the properties are really kind of just Boolean in nature. So there's work to be done there. It's semantically, I think it's, at least informally, it's relatively clear what needs to be done, but it's not so easy to formalize that properly. Okay, then application to other logics. There's a lot of work that's been done on restricted first-order logics by Gabby and a number of her colleagues. I'm not going to go into that. And then a plug for my PhD student, Nick, who's sitting here somewhere. He's done the same, he's taken the same kind of framework and applied it to standpoint logics in various formalisms. In fact, he has 2 papers on this, or versions of this afternoon. So if you're interested, you can go and have a look there. And then I know how much time do I have left? Nothing. Okay. Then I'm not going to go into this in detail. The only thing I want to say is that when we have, with description logics, what works kind of nicely, or the reason it's a nice way in which to lift what was done in propositional logic is because really we're only working with unary predicates. The moment we get to logics where we have n-ary predicates, things get complicated. So this example was intended to indicate that. You can talk to me afterwards about what the problem is in the example. And then the conclusion. So what I've looked at is, I spent a lot of time looking at KLM-style reasoning for propositional logic. It's reasonably well understood. Then I looked a little bit at KLM-style reasoning for description logics. It's not so well understood, but at least we know where the problems are. And then there are some other logics where this can be applied to. Future work, I'm not going to go through the future work in detail because I want to give a little plug as well. Firstly, if you're interested, come and talk to us. There are 8 of us from the University of Cape Town here. And well, I think 8 of them are on this slide. This is a research workshop that we had at the beginning of the year close to the beach. So if you want to come and visit us, this is the place to go. Or this is inclusive, or you can come to Cape KAIR 2027, which is in the first week of February. So then I'll stop. Thank you very much for your indulgence.